you're from the point where I'm holding that brick out the window and let go, the air below the brick is denser than the air above the brick. So it would be easier for it to move into a less dense area. You said
but your potential energy came from which direction? You came from down to up. You took it. You brought it up away from its equilibrium.
Yeah, so there is a down then.
Obviously.
I mean, if I was stood under an arch, arch made of lead, okay, that's denser than the concrete of the pavement. I'm under an arch made of lead. So if I'm holding that brick out, why doesn't it fall then towards the lead? Because that's denser.
Because it's not inside the lid. The air is the medium it's in. It's not inside the lid medium.
Yeah, but what we've got is we've got the medium, the atmosphere, the air, which towards the ground is denser, away from the ground is less dense. So right now we're dropping a brick, it goes towards the more dense. But if we put lead above it, which is a denser medium still, it doesn't fall towards the lead. It still falls towards the ground.
Because it's not inside the lead. The lead
it's not inside the ground either. It's just inside the air.
The air, exactly. It's denser than the air. It took energy to pick it up from the ground. So it's going back to its relative equilibrium.
Let's first look at the problems with density and buoyancy. So the problem number one is things that are more dense and less dense fall at the same rate. And I actually did an experiment with a lead ball and a cue ball. The lead ball was 7 times more dense than the cue ball. And I got up on my ladder and I repeated, and I'll videotape it if anybody wants to see it. And I dropped it again and again and again. They both fell at exactly the same time, every single time.
Identical in size, and the only factor is supposed to be wind resistance. Plain as day.
Second problem with density. Things should fall faster further up as air resistant is as the air is less dense as you go up in altitude. But we know the downward acceleration slightly decreases with altitude.
I wanted to be the first human outside of an aircraft breaking the sound barrier. I died.
So this is what happens to people who only look at the mathematics. Now, I'm not going to call Professor Bryant a liar, but I'm going to call him wrong. If I could have found my cue ball, I could have demonstrated that a lead ball falls faster than a cue ball. I'll give him the benefit of the doubt and say maybe he had a step ladder. I'm baffled that this professor is making these claims boldly. His next claim was that if it were buoyancy and density, things at higher altitudes would fall faster due to lower air pressure. That's exactly what we see. But his globe mathematics tell him that things accelerate at the same rate. But I could have used different examples, but I figured I'd show Felix. But not only that, things get heavier the higher we go. I think it's pretty safe to say that whatever you believe or have demonstrated to cause weight or the downward vector, that density and buoyancy play a huge role. Actually, I should specify, it's safe unless you're using the globe mathematical model.
So it's not this magical, consistent 9.81 meters per second squared every time. That isn't true. That's like a misnomer. I don't know why people say it. But yeah, so it's not just density, but whenever there's a density of an object relative to the density of the medium, that's going to determine direction. That buoyant force that's resultant is much stronger than electrostatics. And in fact, of course, it's even stronger than gravity. Right? Even in this theoretical idea that there's gravity here, this other type of gravity, because actually gravity means gravitas and weights. Anyway, the buoyant force is stronger. It goes up in.
So there's some catastrophic problems with electrostatics. You know, shouldn't we be able to step inside a Faraday cage and levitate? I mean, it doesn't. I mean, we can shield electric charges. Why don't objects of different electrical charge or magnetic properties fall at different rates? I mean, we know this. Different diamagnetic and different, conductors versus insulators. I mean, in electric fields, they would have forces acting on them in different ways. And again, why do magnetic, paramagnetic, and diamagnetic objects all fall at the same rate? So again, you can get a magnet or a non-magnetic object, and gravity will pull them down equally every time. Electrostatic charges can be attractive or repulsive. Gravity is only attractive. So what is the source of this electromagnetic attraction? How does it work if bulk matter is neutral? Electric fields that Austin talked about, they fluctuate wildly, and that at about 30 kilometers, it's almost zero. And we know gravity keeps going beyond 30 kilometers. So it just doesn't work. It doesn't match reality at all. In fact, the electric field changes not only around thunderstorms, but around, the time of day and the seasons. So
you can't have density without electrostatics. So it obviously there's a correlation in density and electrostatics. That's why it's one of the main variables addressed on the chart. But anyway, density itself isn't the full answer. I actually agree with that. Your examples aren't particularly great, though. If you use two different densities and you drop them, well, you drop them from a few feet above the Earth. and they're going to go roughly the same distance down. The primary thing to figure out, what is the determination of the vector? What determines the direction itself? Once it goes down, then, it's agreed upon average. I mean, until you drop something 5 miles in the air in a vacuum chamber, you really don't have much to stand on, and dropping it just a few 100 feet in the air doesn't really mean much. And again, downward acceleration does change drastically. We use gravimeters all over the Earth, and it's different all over the Earth. The downward acceleration of little BB using interferometry. They also have spring-loaded ones. They show different rates, actually. What it does is it sets the bias. So even if we have slight fluctuation in thunderstorms or lightning or whatever, it's very weak. It's very weak. Like when you use a Van de Graaff generator and you make like a little paint chip float or a piece of paper, you can use iron, you can use all kinds of stuff. That's like, those little chips are equivalent to like Mount Everest, right? So the point is that it's very, 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 very weak. It just sets the up and down. That's why you wouldn't see much of a change in downward acceleration, because it would have to be such a drastic manipulation and variance to get any type of difference. But that's not the question. The question is like, what actually causes it to go up and down? And there is no problem with electrostatics other than it's not strong enough to make the Earth spin around. And you said something about at a certain height, right? Like, so you're talking about like at a certain height it drops off. I don't believe any fairy tales above 50, 60 miles or anything like that. But all of it has electrostatics. Even in the globe paradigm, they claim there's something called the ionosphere. And that it starts right at around 40 miles. They say 40 to 50 miles to like 400 miles, which we don't believe stories past 60, 70 miles at all. But the main thing with that is, that was the first time ever that was claimed. Maxwell actually changed his equations, right, to say that you could have electrostatics without matter, because you can't. You can't have electrostatic induction or electrostatics without matter. And they made up the ionosphere to basically save the globe. But the primary point here is we have equipotential increase from the surface up, and that creates a downward flow. And the only way to have that is to have two Gaussian surfaces. So what we know we have on the Earth has to be there because of two Gaussian surfaces, and that is 10 to the 36 power stronger than gravity claims to be. So I don't know why it's so hard for people to accept it, but it just is what it is. And this is why it's not discovered on the quantum scale at all. There's no evidence for gravity on the quantum scale at all. It doesn't work. It's incompatible. The relativity doesn't work at all on the quantum scale. But we know that there's electrostatics there. It's everywhere. And a Faraday cage does not block electrostatics. Sure, it can stop like electromagnetism. It doesn't stop electrostatics. The cage itself is electrostatics. The air inside of it's electrostatics. Whatever objects are in there are still electrostatic. There's still electrostatic induction. And no matter how much you try to neutralize it, like on the very smallest scale, right, which you can't remove it, because if you removed it, you wouldn't have the matter in the first place. On the very smallest scale, it's 10 to the 36 power stronger than gravity claims to be. And 9.8 meters per second squared is agreed upon average. It doesn't happen every time. Objectively, it doesn't happen every time. It changes. It's just an agreed upon average. It fluctuates. But we use that convention so that we can build things like bridges, etc. You can replace little g with the letter A, acceleration. You don't need it. We want to say we have a dependent variable and naturally occurring observable phenomena. Things go down. Things go up and down. So things have direction or different vectors. So what causes something to go down? Well, let's figure it out. Everything that goes down or up, everything that exists in the world is electrostatic. So all molecular and intermolecular attractive forces are electrostatic in nature. So anything going up or down is electrostatic. So let's manipulate the variable of electrostatics and see if it can actually affect the direction something goes. It does, objectively. Things go up and down relative to the electrostatics. The electrostatic field, you have electrostatic induction that goes to the object, and that relationship will cause things to go up and or down. We have all kinds of things that happen in nature that show us this. In fact, bumblebees actually levitate over flowers, and seeing as they accumulate positive charge, which there's actually no such thing as positive and negative charge. You have charge and discharge. It's a convention. There's nothing negative in nature, but that's a different conversation. So it gets positive charge in the air. It floats over the flower that has negative charge, and the pollen will actually levitate up to the bee and stick to it. Clouds, of course, are electrostatic. And then based on the charges in the clouds, that's when eventually the water will come down, right? So based on density and buoyancy alone, or based on gravity alone, there's no reason for those clouds to be up there sitting the way that they do. Now they just claim that it's basically counteractive. Whenever you talk about the Cavendish and you said that they control the variable of electrostatics, in fact, whenever Cavendish first did his experiment, he didn't even account for electrostatics.